This conversation is powered by Google Illuminate. Check out illuminate.google.com for more. Welcome to our discussion on resonance, a fascinating phenomenon in physics. We'll be exploring two technical papers that delve into the topic using interactive simulations. The first paper details a resonance simulator, and the second showcases a simulation model focusing on the effects of damping on resonance. What are your initial thoughts on the importance of studying resonance?
Resonance is crucial because it explains how systems respond to external forces at specific frequencies. Understanding resonance helps us design structures that can withstand vibrations, like bridges, and also develop technologies that utilize resonance for specific purposes, such as tuning musical instruments or medical imaging. It's a fundamental concept with wide-ranging applications.
The first paper mentions a resonance simulator. What kind of information would such a simulator provide? What would a student learn from interacting with it?
A resonance simulator would visually demonstrate how the amplitude of oscillation changes with the driving frequency. Students would see how the system's response peaks when the driving frequency matches the natural frequency, resonance. They'd also observe the effects of damping, how it reduces the amplitude and affects the resonance peak. It's a much more engaging way to learn than just reading about it.
The simulator uses parameters like φ, natural frequency, and Fd, driving frequency. Can you explain these terms in a way that's easy to understand for a high school student?
Imagine a swing. Φ is the natural frequency, how often the swing naturally swings back and forth if you just push it once. Fd is the driving frequency, how often you push the swing. When Fd matches φ, the swing goes highest. That's resonance.
The paper also mentions the different damping levels, light, critical, and heavy. How do these affect the resonance?
Damping represents energy loss in the system, like friction. Light damping means the swing slowly loses energy. The resonance peak is still noticeable, but smaller. Critical damping stops oscillations quickly, no resonance peak. Heavy damping also stops oscillations quickly, even more so than critical damping.
The second paper focuses on a specific simulation model of a falling basketball showing energy transformations. How does this relate to the concept of resonance?
While not directly about resonance, the basketball simulation demonstrates energy transfer within a system. Resonance is about energy transfer from an external source into a system at a specific frequency. The basketball example shows how energy changes form, potential to kinetic, etc., which is a related concept.
The second paper includes an interactive model embedded within a web page. What are the advantages of using such interactive models for learning physics?
Interactive models allow students to actively explore concepts. They can change parameters, see the immediate effects, and develop a deeper intuitive understanding. It's a hands-on approach that complements traditional learning methods.
The paper discusses different cases with varying damping coefficients. What's the significance of observing these different cases?
Observing different damping cases highlights how energy dissipation affects the system's response to the driving force. It shows that resonance is not just about matching frequencies, but also about the system's ability to retain energy.
The paper mentions that at resonance, maximum energy is transferred. Can you elaborate on why this happens?
At resonance, the driving force is perfectly synchronized with the system's natural oscillations. Each push adds energy in phase with the motion, leading to a cumulative increase in amplitude. It's like pushing a swing at exactly the right moment.
The second paper provides several YouTube links illustrating real-world examples of resonance. Why are real-world examples important in understanding this concept?
Real-world examples make the abstract concept of resonance tangible and relatable. Seeing resonance in action, in a wine glass shattering, a bridge collapsing, or a building swaying, helps students connect the theory to practical applications and appreciate its significance.
One YouTube link shows a shaking table experiment. How does this experiment demonstrate resonance?
The shaking table acts as the driving force, applying a periodic force at a specific frequency. Different structures on the table have different natural frequencies. When the driving frequency matches a structure's natural frequency, that structure vibrates with maximum amplitude, demonstrating resonance.
Another example involves a wine glass. How does sound affect the wine glass?
The sound wave acts as the driving force. If the frequency of the sound matches the natural frequency of the wine glass, the vibrations become large enough to cause the glass to shatter, a dramatic demonstration of resonance.
Both papers emphasize the use of simulations and interactive models. What are the limitations of using simulations to study resonance?
Simulations are simplified representations of reality. They may not capture all the complexities of a real-world system. However, they provide a valuable tool for understanding fundamental principles and exploring what-if scenarios in a controlled environment. They are a great starting point for understanding, but real-world experiments are still necessary for a complete understanding. Thank you for this discussion.